Hello and welcome to this Unisensor microsensor lecture. My name is Lars Hauer Larsen and I am CSO here at Unisense and responsible for production and development of Unisense microsensors. In this presentation, I will give you an introduction to how our nitric oxide microsensors are designed and working, which hopefully will familiarize with them and help you applying them correctly. The Unisense nitric oxide microsensor is of the amperometric microsensor type, also known as Clark type sensors, and an in-depth lecture about the working principles for these sensors is available on our website. The lecture will cover the following topics: tip design and detection principles. I will go through the specifications of the microsensor and give some comments to them. Then I will explain how our needle sensors are produced, and at last, I will focus on troubleshooting the sensors. This is a photo of a nitric oxide sensor, and you see here one in action. Details and general theory about Unisense amperometric microsensors are covered in the lecture about Unisense amperometric microsensors, but I will here briefly describe the tip design and working principle of the nitric oxide sensors. The outer tapered glass casing is equipped with a silicon tip membrane. The function of the membrane is to make a barrier between the electrochemistry inside the microsensor and the sample. The membrane is permeable to nitric oxide. If nitric oxide is present, it diffuses through the membrane to the working electrode. The working electrode is a positively polarized carbon electrode, which catalyzes oxidation of nitric oxide. The electrons are delivered to the reference electrode, where a dissolved substance in the electrolyte is reduced. We do not give detailed information about the electrolyte composition and electrochemical reactions because it is a proprietary recipe which is not protected by patents. It is an organic solvent containing a suitable salt. The reference is placed 10 cm away from the working electrode, but for the sake of illustrating the principles, it is included in the schematic drawing of the tip. The current generated is proportional to the concentration of nitric oxide outside the tip membrane, and as the current is very small, in the picoamp range, a high quality amperemeter is necessary for amplifying such tiny current. The guard prevents that impurities in the electrolyte can reach the working electrode, which could otherwise react on the working electrode, and thus the guard electrode keeps the baseline low. The organic electrolyte solution ensures electrical connection between the electrodes and charge balance. The design is optimized to get the highest possible signal to ensure lowest possible detection limit. Nitric oxide is normally present in very low concentration in natural samples, and therefore the membrane is made wide and short to ensure largest possible flux of nitric oxide from the sample to the working electrode. The consumption rate of nitric oxide by the sensor is therefore high, which induces a high stirring sensitivity. The nitric oxide oxidation capacity of the working electrode is not very high, and combined with a large influx of nitric oxide per concentration unit into the sensor makes the linear range very small. I will now turn to the actual performance and specifications of the nitric oxide sensors and give some comments to them. Recall that these specs are only guaranteed with use of a Unisense meter. The detection limit is stated to be down to 2 to 3 nanomolar dissolved nitric oxide for the larger versions of the nitric oxide sensor. However, the detection limit is strongly influenced by the application in question. The smallest sensor, version NO15, generates, due to the small tip diameter, a much smaller current than the larger versions, and thus the detection limit is not better than 20 to 30 nanomolar. The tip size ranges from 15 to 500 micrometers. We produce them in standard models with 15, 50, 100 and 500 micrometer diameter tips. Naturally, the smaller the tip is, the more fragile it will be. The response time is a function of the nitric oxide diffusion path length into the working electrode. To ensure highest possible sensitivity, the tip membranes are thin and thus the sensors are fast responding, especially the smallest, which have a response time of less than a second. Due to the thin tip membrane, we do recommend always grounding the sample in which the sensor is inserted into to avoid ESD-induced membrane damages. I will come back to this. The nitric oxide sensors respond linearly to nitric oxide concentrations at the sensor tip. It will respond linearly up to 3 micromolar dissolved nitric oxide, but it can be modified to measure linearly within a broader concentration range. The limitation of the linear range is determined by the nitric oxide oxidation capacity of the working electrode. Thus, sensors which are produced to measure higher concentrations must have a reduced sensitivity. This is done by reducing the diameter of the tip membrane. The estimated spatial resolution of nitric oxide sensors can be applied with is 2 times the tip diameter. This is just a rule of thumb because it cannot easily be validated. Compared to other Unisense amperometric sensors, the large consumption rate will to a higher extent deplete the analyte at the membrane/sample interface. So compared to other Unisense microsensors with a very small analyte consumption rate, the sensor will sample nitric oxide from a larger diffusion sphere at the membrane/sample interface, in which the natural concentration will be affected by the sensor consumption. So the sensitivity to steering is for standard nitric oxide sensors more than 20%. The sensitivity to steering is defined as the difference between the signal in stirred and stagnant sample with the same nitric oxide concentration. This is exemplified here where a sensor measures in a continuously mixed sample. When the steering is stopped, the signal decreases more than 20%, which is typical for a standard range nitric oxide sensor. And when the steering is reactivated, the signal is back to the original level. The large sensitivity to steering will typically result in unstable measurements in nitric oxide containing samples. The lifetime is expected to be 3 to 6 months, sometimes more, provided that they are not physically damaged. Typically, they are sensitive to nitric oxide much longer, but with a decreased performance. Over time, the working electrode loses catalytic efficiency, and as a consequence, the sensitivity decreases. The loss of sensitivity is not a function of measuring time, it is simply a function of time. The loss of working electrode efficiency causes drift. In combination with settling diffusion coefficients through membrane and electrolyte, the drift could be up to 20% per month, but also less than that. The sensors are handmade, so variations must be expected. We do therefore recommend calibrating as frequent as possible. Physical impact to the sensor can, besides destroying the sensor, change the sensitivity and thereby the calibration curve of a nitric oxide microsensor. The working electrode connects to the amperometer via a thin, flexible glass-covered platinum wire. Physical impact, which shocks the internal components, can induce a displacement of the working electrode position relative to the membrane and thereby changing the sensitivity. Typically, such impact will induce a sudden signal peak, followed by a stabilization time. But the sensitivity might not return to the original sensitivity caused by a displacement of the working electrode position. The baseline is normally not affected. Nitric oxide sensors stand up to 5 times atmospheric pressure without being pressure compensated. However, as other Unisense microsensors and electrodes, we can pressure compensate the inner parts of the sensor so they do withstand full oceanic pressure. When pressure compensated, they are tested to be able to withstand 600 bars. In the web lecture about amperometric microsensors, the temperature influence is discussed in detail, and it is explained there why temperature compensation is difficult for amperometric microsensors. Temperature interference is about 2% per degree Celsius. We therefore recommend calibrating the nitric oxide sensor and measure at the same temperature. The sensors can be used from 0 to 40 degrees Celsius. At higher temperatures, the baseline and noise level increase and compromise the sensitivity. The temperature influence on the baseline is huge and much larger than other Unisense sensors. Therefore, temperature control, especially when working at temperatures above 30 degrees Celsius, is of extreme importance. I will not in this presentation go into details with all the adaptations and modifications we do to the nitric oxide sensors. This is covered in the quick guide, but I would at this point describe how a needle-embedded sensor is made. We make needle-embedded versions of the nitric oxide sensors in order to give some protection to the sensor tip from being damaged. We make them in two different versions, nitric oxide N and nitric oxide NP. The latter is made for piercing membranes. This is a schematic drawing of the tip of an NON and an NONP sensor. The needle protects to some extent the glass, but the sensor tip is still fully exposed for the sample solution. The needle and the glass part of the sensor are glued together inside the needle, so no sample liquid will intrude into the needle. This would otherwise cause a huge carryover effect. I now turn to troubleshooting nitric oxide microsensors which do not exhibit normal performance. Naturally, a small glass tip is fragile and the tip might break if it hits something hard. A broken sensor will in water give a very high signal, typically out of range, as the working electrode is now directly exposed. So, if the tip breaks during measurements, a sharp signal rise will occur to the out of range signal. It is not possible to repair a broken sensor. If the tip gets biofouled or covered with sticky polymers, it might measure incorrectly. The tip tolerates almost all possible cleaning substances like alcohols, acids, detergents, proteinase solutions, etc. So it is recommended to insert the sensor into different cleaning solutions to see if this solves the problem as the first attempt to remove the foul. The tip should only be dipped into alcohols for a short period of time, as short-chained alcohols like ethanol can pass the membrane and affect the electrochemistry. If chemical cleaning does not remove the fouling and restore normal performance of the sensor, a physical cleaning is the only solution. For NO50 and larger sensors, it is safe to wipe the tip with a piece of soft wetted fabric or paper. If you hold the sensor so the tip points away from you, the wipe direction must always be the direction the tip points, never against the tip, which will impose a risk of tip damage. For the NO15 sensor, physical wiping might break the tip. For physical cleaning of these fragile sensors, we recommend that you hook the sensor up in a microprofiling system and gently insert the sensor in a soft matrix, which gives some shear force on the fouling material and removes it. The best material we know of to do this is Oasis flour foam. It should be wetted before inserting the sensor. Alternatively, it is also possible to insert the sensor tip in an agar gel. This is less efficient but also totally without risk. These curves illustrate a normal startup behavior of a nitric oxide microsensor when connected to a Unisense amplifier and polarized. The signal is high and downward drifting right after polarization due to unspecific reaction on the working electrode. If there is not such an initial peak signal, but instead the signal does not rise much from zero, it might be due to a gas bubble stuck in the tip and which disconnects the working electrode from the reference. There must be an air/gas phase in the electrolyte cavity in order to make room for temperature-induced expansions of the electrolyte. And if the sensor package is turned upside down during shipment, a gas bubble can be trapped in the tip. Such air bubble can be removed by shaking the sensor like it is demonstrated here. The bubble will become loose and rise to the top of the electrolyte cavity and the connection will be restored. In rare cases, a gas phase can evolve in the tip at the position of the working electrode, and such gas cannot be removed by shaking. So, if the sensor do not give any signal, this could potentially be the explanation. Such gas phase can easily be removed by inserting the tip into degassed water, which will drag the gas out of the tip through the membrane. So fill water into a glass bottle and boil the water. This drags gases out of the water. Let the water cool to a room temperature or below without shaking the bottle or mixing the water. Place the sensor tip into the water for some hours. The gas phase will be removed by this procedure. If a sensor experiences a physical impact like a drop on a table, the working electrode could be displaced. If the displacement results in a working electrode retraction from the silicon membrane, the signal will be slow and sensitivity low. The sensor will still be nitric oxide sensitive, but has lost its original behavior, illustrated here by a before and after incident. It is unfortunately not possible to restore original performance. A physical impact like a drop could also damage the glass insulation of the platinum wire connecting to the working electrode. This will typically result in an elevated and noisy baseline due to exposure of polarized carbon to the electrolyte. Chemical reactions taking place on the exposed carbon surface will create a current which will overlie the working electrode generated current. The size of the baseline increase will depend on the degree of damage to the carbon wire insulation. Such damage cannot be repaired. The nitric oxide sensors have thin membranes, which can be vulnerable to electrostatic discharges. A charged person who touches, for example, a beaker in which the sensor tip is placed, can induce a potential difference of thousands of volts across the membrane and potentially induce a discharge which destroys the membrane. To be sure that this does not happen, a grounding wire should be connected to the liquid or setup in which the sensor tip is placed to the ground socket of the Unisense amplifier. A sensor with a damaged tip membrane will have a very unstable signal, strongly affected by electrical noise. By grounding the sample or experiment to the ground socket of the amplifier, the signal will stabilize. A damaged membrane cannot be repaired. Thank you for watching this Unisense microsensor lecture. I hope you enjoyed it. If you have any questions, you are more than welcome to contact us at sales@unisense.com.